So the three examples that we have left, and we'll do one of them today, are both going to use different geometry formulas. Obviously, example 3, I labeled it for you. Example 3 is going to use the distance formula, and then examples 4 and 5 are two somewhat complicated examples, but they use the Pythagorean theorem. There's something really important with our distance formula that's going to make our lives easier that we'll talk about when we get there. But the question is basically asking us, what point on the graph of the function y equals square root of x is closest to the point 5, 0? So the question that we're sort of answering here is, if I drew a straight line from my point 5, 0 to anywhere on the graph of y equals the square root of x, where's my shortest line? You might think it's straight up and down. You might think you might be able to diagonal it a little bit. It's clearly not going back over here, right? That is definitely longer than going straight up or sort of to the left. So that's kind of what it ends up being. It ends up being, somewhere on a diagonal, and we'll find that exact point. And since we're trying to minimize distance, that's why we're using the distance formula. So some of us didn't get a lot of geometry because of COVID. Does anybody remember what the distance formula is? Yeah. Close. Yeah. Yep. Yeah. It's a variation of the Pythagorean theorem. Because basically what this subtraction is doing, you're basically trying to find the hypotenuse of a triangle, but these are the sides. You've got to do this subtraction to figure out how long they are. It is also, yes, sorry, they are both squared, yeah. And it's a plus in the middle. There we go. I think I heard the plus. I think it's just, that's an easy one to do too. You just get mucked up in all of the pluses and the minuses, but you're subtracting your coordinates and you're adding your results, because in the end, this is C, just like the Pythagorean theorem, this is C equals the square root of A squared plus B squared. You just have to do a little math to get your A and B. Okay, if we had more time, I could draw a picture of that, but it's a takeoff on the Pythagorean theorem. So what the heck are our x2 and our x2 and our y2? One of those things is going to be the points. So it's probably easier to make the x1 and the y1 numbers because because they're being subtracted. So I'm going to call my point x1, y1. And then my x2, y2 are going to come from the function. So I'm going to use x for x2, and I'm going to use the square root of x for y2. The reason that is you can kind of call any generic point on the function y equals square root of x. Whatever x you plug in, the function is going to be at the square root of x. So that's going to be your x2 and your and your y2. Okay. So a generic point on the function would be whatever the x coordinate is for x and the square root of that x coordinate for y. So we're going to plug all of this in, and we get d equals the square root of x minus 5 squared plus y minus 0 squared, which is not y minus 0 squared, but square root of x minus 0, which is basically squared. Yep. Okay. Okay, so here's the important part with these problems. We need to maximize this, which means we have to find the derivative of this. We'll simplify it a little bit, but the square root's going to be a pain in the neck. But it's going to turn out we can actually find the derivative of a simpler function that's going to have the same critical value. So we'll get that. Let's get ourselves cleaned up here, though. So we've got d equals the square root of x minus 5 squared. So we'll do that. We'll do x squared minus 10x plus 25. And then the square root of x minus 0 squared is going to be just the square root of x squared, or just plus x. So really we have the square root of x squared minus 9x plus 25. The nice part about both of these functions, this function is that wherever x squared minus 9x plus 25 has a maximum, the square root of x squared minus 9x plus 25 will have a maximum. So rather than having to find the derivative of this, which would use the chain rule, we could actually just find the derivative of the inside of this one. So it's a little bit of a shortcut with these distance problems. I was sure there weren't going to be announcements with keystones today. So we are going to minimize, or, yep.
Standing for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
The minimum value of this, the x value that minimizes this, will also minimize the square root of this. Okay? And that's easy. So we're just going to take its derivative. I can't believe they're doing announcements on a Keystone Day.
My name is Carrie, and I'm Kezia, and here are your announcements. Happy National Trivia Day. What year did West open? Yearbooks are now
2001.
available for purchase online by using the link that cancel code /3002. They can be purchased for $50. Customization is available for additional costs. This is the rarest the yearbook will be this year. Last year's books can be on sale, so our discount price is $40.
So I wrote it out because I'm not talking, but took the derivative, got 4.5, solved. There's your shortest distance right there. Does that make sense? Okay. That extra part, you know, if you did this derivative, you would end up basically, because of the chain rule, having this in your numerator, and you'd end up doing the same thing. So it's a little bit simpler whenever you're working with minimizing or maximizing a square root, just minimize or maximize the inside. A little bit of a shortcut there. Cool.